Welcome back, Focus Learners. Today, we are diving deep into something truly special, an explainer designed to completely transform your approach to the exam. We're going to master one of the most notoriously tricky areas of the Cambridge syllabus, specifically tackling the demands of Syllabus 9618 and even looking back at the foundation built in past papers like Code 9713. And we're going to do it by shifting our perspective entirely. We are going to start thinking like a master photographer. Now, if you think about it, a professional photographer doesn't just walk into a room, point a camera blindly, and press the shutter. That would just create a messy, unfocused image. Instead, what do? They survey the scene. They find the absolutely perfect angle. They carefully frame their subject, intentionally cutting out the background noise. They adjust the lighting to highlight the absolute most important evidence in the shot. Your approach to constructing logic circuits from problem statements needs to be exactly the same. When you are faced with a massive, intimidating paragraph of text detailing a complex system, you can't just start blindly drawing shapes. You need to frame your answer to highlight the key evidence. In this explainer, we are going to unpack the ultimate strategy to find that perfect angle every single time, ensuring you extract every possible mark from the examiner. So I need you to grab your notebook, put your phone on silent, eliminate those distractions, and let's get completely focused.
Here is our structured roadmap for today. First, we'll outline the logic circuit challenge. Then, we'll break down the core cognitive domains and build out your procedural framework. After that, we'll sharpen your critical evaluation skills, learn the secrets to earning method marks, and wrap up with the top examiner warnings. I want you to listen very closely to this direct quote pulled straight from the Principal Examiner Report. They state, "Constructing logic circuits from problem statements is one of the most misunderstood areas in computer science." Let that sink in for a second. This isn't just a random opinion from a teacher. This is the definitive consensus from the people who actually grade your papers. If you've ever sat in a mock exam, looked at a dense paragraph of text describing an automated greenhouse or a complex factory alarm system and felt your mind just go completely blank when trying to draw the logic gates, I want to validate that struggle for you right now. You are absolutely not alone. The senior examiners themselves are openly acknowledging that students universally stumble here. It's a massive roadblock. But here's the exciting part. Understanding exactly why it's so widely misunderstood is our very first step to conquering it. It's essentially a translation issue. You are being asked to act as a bridge between plain, everyday English and strict mathematical Boolean logic. And bridging that gap requires a very specific toolkit that most students are simply never taught.
So let me ask you this directly, and I want you to really reflect on it. Why do students find multi-step calculations and method marks so incredibly hard? Think about your own past paper practice sessions. When you see a high-value 6-mark question asking you to derive a Boolean expression and then construct a full circuit from a real-world scenario, do you freeze up? Usually, the root cause is that the cognitive load is just too massive. Your working memory gets completely overwhelmed. You are simultaneously trying to read and translate a paragraph of plain English into logical conditions, while also trying to remember the distinct physical shapes of the and, or, not, and XOR gates. On top of all that, you're trying to format the circuit perfectly on the page so the wires don't cross in a confusing way. When your brain tries to juggle all those distinct tasks at the exact same time, the system crashes. The brain gets overloaded, the angle gets blurry, and the framing is totally lost. To fix this, we have to isolate the process. To really see this dynamic in action, let's look at two very common student profiles. Let's call them Alex and Sam. First, we have Alex. Faced with a complex logic scenario, Alex's immediate reaction is panic. To overcompensate for that panic, Alex overloads the page with raw computer science facts. Alex draws out massive, complicated truth tables that the question never even asked for. Alex writes down textbook definitions of what a logic gate is, hoping to scrape a mark. But Alex completely fails to analyze the specific problem statement provided. It's an unfocused photograph capturing everything but the actual subject. Then we have Sam. Sam is the complete opposite. Sam reads the first sentence and thinks, "Oh, I know this immediately." Sam rushes. Because of that rush, Sam entirely misses the specific command word requirements at the start of the prompt. Sam doesn't notice the critical difference between draw the circuit, explain the logic, or derive the expression. Sam skips crucial intermediate steps, just throwing down a final answer that has major flaws. Here's the tragic reality. Alex loses heavy marks for a complete lack of targeted analysis. Sam loses vital marks for blatantly ignoring the command words. Both of these flawed angles cost them vital points, and we see this exact same tragedy play out whether students are sitting the advanced 9618 syllabus or building their foundations in 0417, 0478, 0983, 0984, or 2210.
Let's move into Section 2, the strategy reveal, where we focus on mastering the core domains. Before we continue, subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, let's break down how to actually build your fundamental understanding and avoid the traps that caught Alex and Sam. You need to realize that the examiners are targeting 3 distinct assessment objectives, or cognitive domains, when they throw a logic circuit problem at you. First up is knowledge and understanding. Simply put, do you know the raw facts? Do you know what an XOR gate does versus an OR gate? Second is application. Can you take that raw knowledge and apply it to a completely novel, specific scenario? Like, say, a factory conveyor belt sensor that only triggers when a box is present and the weight limit is exceeded. Third is analysis. Can you systematically break down a complex, intimidating paragraph into discrete logical conditions? The absolute top-tier students conquer all 3 of these domains by relying on the Peel framework. Now, you might know Peel from essay writing, but yes, it applies perfectly to computer science. Peel stands for point, evidence, explanation, and link. When you answer a logic circuit explanation question, your point is identifying the specific logic gate required, your evidence is quoting the exact phrase from the problem statement that proves you need that gate, your explanation dictates how the specific inputs combine at that gate, and your link connects it all the way to the final output of the system. If you frame your mental process using this exact Peel structure, you perfectly satisfy those 3 cognitive domains every single time, proving to the examiner that you aren't just guessing.
Now, what's really genuinely interesting here is understanding the concept of the method mark strategy. This is a game changer. Marks are awarded for the process. In constructing logic circuits, I need you to hear this loud and clear. You do not have to have a perfectly pristine, flawlessly correct final circuit to get a really good score on the question. Let's say it's a 6-mark question. If your final output is completely wrong because you messed up the very last gate, but the examiner can clearly see that you correctly translated the first 2 sentences of the problem statement into a valid and/or cluster on the left side of your page, they will give you method marks. Method marks fundamentally relieve the crippling pressure of needing a perfect final answer. They reward your systematic process and your evidence-based reasoning. This is exactly why you absolutely must show you're working. You must leave a clear, undeniable trail of breadcrumbs for the examiner to follow, so they can award you points for the steps you got right.
Section 3, the procedural framework. Let's look at algorithmic thinking in action. To absolutely guarantee that you secure those method marks, here is your 5-step procedural breakdown derived directly from analyzing top-scoring exam papers. Step 1, identify key elements from the text or binary representations. You underline the variables. Step 2, apply relevant principles. This means translating those English words into the correct logic gates. Step 3, execute analysis. Draw it out with clear, deliberate working. Step 4, verify your results. Don't just assume you're right, test it with a quick mental truth table. Step 5, present in the appropriate format. Ensure your gates are drawn clearly and wires are distinct. I challenge you right now to create a memory hack, a simple mnemonic, using the first letters of these steps, IAEVP. Maybe something like, identify all existing variables perfectly. Lock this specific IAEVP sequence into your brain. Imagine taking those red penalty marks that Alex and Sam got and systematically converting them into green check marks. If Alex had used this framework, Alex wouldn't have drawn unnecessary truth tables. Alex would have stopped at step 1, identified the key elements, and moved forward logically. If Sam had used this, Sam wouldn't have rushed past the command words. Sam would have verified the results before moving on. When you open that exam paper and the panic tries to set in, you don't let it. You just execute step 1, identify.
The crucial point tying all this together is defining exactly what algorithmic thinking means in the highly specific context of logic circuits. Your syllabus defines it as step-by-step decomposition, appropriate data structure selection, efficient code implementation, and rigorous testing. In our specific case with problem statements, decomposition is the magic word. It means reading a massive, scary paragraph and aggressively breaking it down sentence by painstaking sentence. When you read, if the temperature is too high and the water level is low, you immediately recognize that as an AND gate. Boom. You've decomposed a complex sentence into a simple Boolean operation. You aren't just memorizing definitions anymore. You are actively engineering a solution. Section 4, Interactive Workshop. Let's put this to the test with critical evaluation and data scans. Stop scrolling. Subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's jump straight into Challenge 1, the data scan. When you are asked to evaluate the quality of an algorithm or a logical system, you have to consider 4 critical metrics: time complexity, space complexity, edge cases, and effect on overall performance.
I want you to imagine a 60-second visual countdown timer ticking away right now. The pressure is on. When you evaluate a logic circuit, you must instantly scan for these metrics. But pay very close attention here. For logic circuits in particular, edge cases are the ultimate trap set by examiners. What happens to your circuit if all inputs suddenly become 1? What happens if a power failure makes all inputs 0? Examiners absolutely love to hide incredibly tricky scenarios deep in the problem statement, conditions that only trigger under these bizarre edge cases. You have to train your brain to stop looking just at the normal operating conditions and aggressively scan for the extremes. Moving right into challenge 2 and 3, let's look at the ultimate problem-solving loop: deconstruct, solve, evaluate. Imagine we have a 30-second timer going, and we are doing a speed writing challenge. If you needed to write an explanation of a circuit, you would use this exact cycle to frame the perfect PEL paragraph. First, deconstruct. You identify the given information in the scenario. Second, solve. You break it into logical steps and literally draw the gates. Third, evaluate. You rigorously check your work for reasonableness. This evaluation step is where you find the flaw before the examiner does. Let's say the problem statement explicitly says the motor turns off when the safety switch is pressed. Well, your evaluation step should mentally trace a 1, representing the pressed switch, all the way through your drawn gates and verify that the final motor output actually becomes a 0. If it stays a 1, your circuit is flawed. You evaluate, you find the error, you fix it, and you secure the mark. Section 5. Inside the examiner's mind. Here are the top 3 warnings you need to look out for. We've essentially stepped directly into the examiner's grading room to reveal exactly where students hemorrhage points on these papers. Based on the reports, here are the top 3 warnings. Number 1, confusing cause and effect. Number 2, forgetting boundary conditions and edge cases. Number 3, providing generic, non-contextual answers. Let's really emphasize that first point, because it is incredibly dangerous and so easy to do. Confusing cause and effect in a logic circuit means you fundamentally mix up your inputs and your outputs. For example, you might read a statement like, "The alarm rings if the motion sensor triggers," and in your panic, you accidentally wire the alarm as an input. It sounds silly when we say it out loud now, but under the immense pressure of the ticking clock in the exam hall, it happens constantly. You must clearly isolate your starting conditions, your inputs, on the left side of the page, and your ultimate effect, the output, on the far right. And this brings us to a brilliant illustration of the most classic mistake of all: generic answers versus context-specific answers. Generic answers are heavily penalized by examiners, while context-specific answers are richly rewarded. If the exam asks you to explain the logic of a safety circuit for a chemical plant and you just write, "An AND gate outputs 1 only when both inputs are 1, you will lose the mark. Why? Because it's generic. The examiner knows you just memorized the textbook definition. You haven't demonstrated any actual understanding of the problem. To get the mark, you must be the master photographer. You must frame the specific subject of the question. You must write, "The AND gate outputs a 1 to activate the cooling system only when the temperature sensor and the pressure sensor both output a 1. You see the difference? You must deliberately link every single logical point back to the given real-world scenario. Finally, Section 6, the final system. Let's lock in how we are securing top marks. Think of this as your ultimate cheat sheet recap. Here are the 3 non-negotiable rules that guarantee top marks in your computer science exams. First, decode command words. Never rush into an answer like Sam did. Know exactly what construct, derive, or evaluate actually requires you to do. Second, apply the PEL or procedural framework. Deconstruct, solve, evaluate. Frame your answer logically, point by point. Third, focus entirely on the method mark strategy. Show you're working, systematically process the text, and capture every single process point available along the way. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. I want to leave you with one final provocative thought. You now possess the lens, the angle, and the exact framing technique that top students use. The rest is entirely up to your execution. Ask yourself, in your very next practice paper, will you be the panic student wildly overloading the page with random facts, or will you be the master photographer, calmly finding the perfect logical frame? Brilliant exam results aren't about pointing and shooting in the dark. They are about structured, algorithmic focus. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the exams. Your Cambridge success starts here.